So also what I will present today is about a work that recently was published in this Indoor Environment, a journal that is dealing about environmental hazards, risk, health, considering mostly the impact on the place where we mostly stay, so that is the indoor. So let's see if I can move. So a little bit of introduction. So who I am. My background is in chemistry. I was doing my PhD in environmental science, and I was mainly working on environmental monitoring. I was then a Marie Curie postdoctoral fellow at the University of California, Berkeley, where I joined a group that it was mostly doing wireless sensor networks in the built environment. So my goal was to learn how to work with many sensors to be able to build. This was the idea, and what I'm interested to do, like a wireless sensor network for environmental monitoring. And now I am a researcher at the Institute of Polar Science. So what I'm doing, I think I was thinking, because there are like many different aspects of the work that I'm going to show you here. But I think that if I can summarize it, I will say that I'm trying to do environmental health. And I think this is important for me, not only because I think it's more being healthy is not only about being healthy ourselves, but it's also being in an environment that is healthy. And I think this is actually the base on which we can build some other stuff that we like to do. But from another side, I think I also like the idea of considering health together with the environment, because I think it could be the right approach to drive better behavior that we have like in our societies, and especially in cities, and you will see some more about this. Because I think if we want to have be more climate resilient or environmental resilient and sustainable, as a society, I think we should consider something that we usually don't consider much. That is actually the behavior, or the bad behavior that we have, that is creating the most impact, both for our health but also for the environment health. So the environmental, we'll like, for instance, environmental pollution for say one, and climate change. So that's to say, like, when we talk about how to improve sustainability of resilient society to, let's say, climate change, and this article or this work is talking about wildfires. So it's all this discussion, but is like now focusing on one problem. Wildfires are, and this is of course in California, because this is the work that I was doing while I was there. So wildfire is a big concern because of the billions of dollar losses that we have, that California is facing every time they have a wildfire, and is also the main source of particulate matter air pollution in the western US. And fine particulate matter, or PM2.5, is also the enemy number one, where we are talking about premature death due to air pollution. And because of climate change, we are expecting an increased risk of wildfires by 2050 relative to 2000 level. So wildfire is one of the big concerns that we have today, and something we can build like a more resilient society we need to do it in the future. Just like a very super quick recap, I'm not talking a lot about the chemistry of PM2.5, just to say that PM2.5 is a big concern because of its size, that basically is able to reach the bronchial region, and even particles that are even smaller than 2.5 micron can actually enter the bloodstream. So there is like a lot of literature about how the different health impact that we have about being exposed to PM2.5, not only about the lung cancer, but also other kind of ischemic attack, heart attack, other systemic issues, even in fetal studies that is showing how exposure to very fine particulate matter can even affect the fetus. So PM2.5 is a concern, and about what you should do during the wildfire event. So the EPA, the Environmental Protection Agency in the US, has a very neat document that is showing about the best practices that you should, what you should do during the wildfire days. And here is an example of San Francisco during the 9 or 11 September 2020, that basically the sky was red and the air pollution was like way over the limit, about 300-400 microgram per cubic meter. And so what you should do is like sheltering indoor. So the building are your first line of protection from PM2.5. So close yourself in, close the windows, and use a portable air purifier if you have one. And then if you also have in the house, use mechanical air ventilation with an high efficiency filter. But there is like a limit on this policy that that they have in California. But the real barrier is that you cannot control if people are actually following the guidelines. So you have beautiful guidelines, very well done. If you go look for prepare yourself from wildfire smoke from the EPA, is very beautiful with infographics. But there is like the barrier is, are actually people knowing about these infographics, these best practices, and are actually acting in the correct way. So what we will try to do is to understand this kind of behavioral barrier. But before I go to the objective, I also want to recap, because I think this is something that we are not much exposed here, or that's at least what we are not together. So I cannot ask you to raise your hand if you know what is a mechanical ventilation system. But so I will just summarize that air purifier is a fan that is creating a depression in a system that is basically dragging in air passing through a filter. The filter has some efficiency in removal some particle, for instance PM2.5, and then some clean air is going to be delivered in the room. The mechanical ventilation can be assumed kind of a similar. You have like a fan. This fan has a filter, is delivering supply air, clean air in each room, and then there is, let's say, a return duct that is bringing back the air into the unit. So if you close all the outlet and all the inlet, basically your entire house, if you have this mechanical ventilation, is a mega air purifier. And that's why there are like some studies that shows that actually mechanical ventilation can have a co-benefit, not only for protecting for extreme heat, but also for having a health impact effect of reducing exposure to fine particulate matter. So what we are doing as an objective is to study how households were using their mechanical ventilation system during the wildfires, and also on the way define some best practices for reducing the indoor exposure to wildfire PM2.5. And the data we used, we decided to do this analysis because in California there are like this open data. Let's say all the companies want to also are more like prone to work with open data, and so this ecobee thermostat, the one here on the right, was releasing the data of the runtime of their users. Of course, with some privacy, so we didn't know about which household, etc. But we could know about the runtime, and also we can also see if they are changing the setting. And we use this kind of changing of the setting as a proxy of the occupants' behavior. And yeah, so the data set we used is here you can see on the left. So the households are about 5,000 homes, and we use the NOAA monitor for meteorological data, and we use the EPA station for the air quality data. And in California, they have a very nice network. Basically, every homes in California lives at less than 10 kilometers from a NOAA or a EPA station. And here on the right, you can see the distribution on the y-axis. You have the percentage of the households that we analyzed, and on the x-axis you have the hours that the system is running. And if you see the distribution, basically between non-wildfire days in blue and wildfire days in yellow, there are not really like a change in the HVAC use. And actually, if we can see a change, like a statistical change that we can actually measure, is going into the wrong direction. So people are less using the heating and ventilation system during wildfire days, despite the wildfire days. So that was the first result that we were saying, okay, there is a regulation, but people are not actually doing the right things. And also here, the wildfire days is defined as a day where the average daily average concentration of PM2.5 is above 35 microgram per cubic meter, and is let's say like a rule of thumb that is used from EPAs and other agencies in California. More than this just a runtime, we were also looking now at how people are changing the setting. And so here in this plot, you can see that the more greener the area, or the more stronger the color, the more are the change. So people are like actively interacting with the thermostat. And the trend here is the trend of outdoor air temperature. And this makes sense. I mean, everybody knows that the thermostat, you want to use it when you want to cool or to heat. So it's quite obvious that we can see this increase correlation between the temperature and the interaction with the thermostat. But again, we saw that there is no relationship between the interaction that the user has with the thermostat when there are like days that has a very high daily average concentration of PM2.5. So the take-home message is that despite we might have very good science regulation, infographics, and etc., until you are not able to reach the citizens, you don't see an effect. And in this case, you have a social and health cost due to this misbehavior. So now that we saw, okay, people are not using the mechanical ventilation system, but can we do an estimation about how much this is, how much is the cost of not doing that, the health cost, the societal cost? And so for doing this, we actually enter a field that took to me about more than, I would say, 2 years to complete this work. And so we built a mass balance model that was able to estimate the infiltration of air from the outdoor to the indoor. We estimated the air flux that go into the dry deposition. Of course, for balancing, you need to consider to model the exfiltration of air. And in case you have a mechanical air ventilation system, based on many assumptions that we can discuss in detail if anybody is interested, but to here just to say, you can dimension for each of the California climate zone how is the size of the fan, and so estimate the fluxes that go into this circuit, and you can estimate the amount of particle that can be removed by the efficiency of this filter. So with this mass balance model, that we also built with the experts in the field, like HVAC engineers that were in Berkeley and Davis. We created the most representative homes for each of the California census tract that you can see here, just a zoom in the Bay Area. So for each tract is the smaller representative area in California for which you have information about buildings. And this is the information you have from the community survey, so basically the census, and from information that you can get from the climate zone, from the ASHRAE, from the building companies, and etc. So now what we did is to make these most representative homes for each of the census tract, and then run some simulation to understand what could be the benefit of using a mechanical ventilation. And this is an example for one home in a few days. And so on the top, you can see the outdoor PM2.5 concentration from the most closer EPA monitor, and the outdoor air temperature, the red dashed line that is coming from the closest NOAA monitor. Here you see this dashed line that is 35 micron per cubic meter, and is this threshold that here we're not using the daily average, but we are considering when we are above or below this threshold in the for each timestamp that we are considering. Here you see that you see here probably is hourly average, but during the simulation we were using 10-minute intervals. And so I choose to show this example because we have a situation in which we are above and below the threshold. And here on the bottom, you can see the air conditioning operation, the average for this for the tract, that is mostly the average for the county. And so when the system is running, the air conditioning, you have this jump going up to 1, and then when it's off, it's going to 0. So basically here you can see when the system is running because of cooling, especially this is very correlated with the higher air temperature. And then what happening in between are the simulation. So using the model, you can simulate what happens if you just shelter indoor, and this is like the highest, the curve in above. So this is the best that you can get to, but just sheltering indoor, closing windows, and estimating the infiltrated area due to the leakage that the building has. The air conditioning is the co-benefit that you have, the green line, when the system is running for cooling. So you are running the system for cooling, and because the air is going through a filter, you have a co-benefit from the health point of view. And then we are able to estimate also the portable air cleaner, in this case only one, and use an average commercial characteristic of a portable air purifier. And then the wildfire mode is what we call it wildfire mode. Is not something existing. It's like how the way we describe this system. That imagine if the system is also working when the PM 2.5 outdoor is above a threshold. So in this case, you see that as soon as the concentration goes above 35 microgram per cubic meter on the outdoor monitor, the system inside the house is starting without air conditioning operation, so only air recirculation, and you have a dropped limit reaching, let's say, an equilibrium with the air that is coming inside, and the efficiency of the filter to remove it. And you see that is as soon as the system going down, the wildfire mode is not working, the indoor concentration going up, and then it's starting again and dropping down again. So with this kind of model, we basically, we can say that a rule of thumb is that a residential mechanical ventilation system can be as effective as about 4 air purifier on the average for California. And if we see, like for the entire northern part of California, so this is just the average. I'm not showing the error bars here because it's very noisy, but I will show you later the sensitivity analysis. If we take the average PM2.5 concentration for all the North California that was affected by wildfires, this is the mean, and the effect of like sheltering indoor, using a portable air cleaner, using air conditioning co-benefit, and using this wildfire mode has a different effect. So you have a huge effect by just sheltering indoor. You have like an increased benefit until we reach like the best that you can do using a system when you mostly needed. You have a almost 90% reduction of your indoor exposure. And I think this is also like a good KO message for when I'm discussing with a health partner now, is that a lot of the health impact assessment that are done today are considering outdoor averages over like a long time period, for instance, a year. But actually we should, the more we are building more energy efficient homes, the more the indoor environment start to be different from the outdoor environment. And so starting to understand what is the exposure of people in the indoors is becoming a real need. And so here I was not showing the errors, only here in the box plot on the right, but we did many simulations because we cannot, we didn't have enough money to do like a case study. It's very difficult to install monitor in, let's say, many homes. So for now, what we can do is only do a lot of sensitivity analysis. So on this 9,000 simulation with this model that I showed, we did additional about 190,000 simulation, changing like the house floor area, the effective leachate area of the building envelope, the starting point of the indoor and outdoor, the type of system filter, the type of runtime used. And so here I show like one of the plot that is like showing that basically you have on the bottom left the worst case, like the most the less efficiency filter, the most basically the filter, and let's say here you have like the most leaky home, and here the most airtight home, and here this one on the bottom side are houses that are small here in size. Let's say these are like medium houses, these are large houses. So there are like reasons why large homes has a more surface, so usually have a better deposition indoors. So you also have a benefit of having a larger volume, and so you have like usually like a better indoor air quality. And so with this data, and also with this kind of estimation of error, we also did this health impact analysis. So using the wildfire mode control, basically we estimate our reduced risk mortality about 76% in the 2-month period used. And for this 2-month period, we estimated $29 million in benefits. That our benefits are calculated due to less hospitalization, and things like that. I'm not really a health expert. Some of the colleagues like Chayum was, and this is something that I'm very interested to dig more like in the future. And this estimated benefit are like also you need to consider the more energy that you're using, and this is about $5 in the bill, in the energy bill for each household. So a person using this wildfire mode during the 2 months of the wildfire season in California was spending $10 more for using the mechanical ventilation system for air quality purposes. And what we found that it was actually kind of expected also is that the greater potential to reduce health impact you have it in areas where lower income households lived. And this is because this area, usually people that has more money lives in areas that are like nicer with better air quality and with better homes. So the more you are like on the low side of the lower income part of the society, the more is that you're living in an area that is more polluted. For instance, here in the San Joaquin Valley, in the Central Valley, and your house has a less quality of building. And this is particularly true in California or in the US. And here, if anyone want to talk a little bit, we can also talk about the how you calculate this health impact using this concentration response function. That is the one here on the bottom right side of the slide. And about this the cluster analysis, also we tried to see like if we're able to clusterize the region in California, considering the number of wildfire days here on the x-axis and the income on the y-axis. And what we see is that we have this clustering. So near wildfires, you have the best reduction of using this wildfire mode, but it's also the area where you have a less population. So the most important part is that you can actually achieve a 5 micron per cubic meter reduction in the potentially exposure in the Central Valley, where the 21% of population California lives. But you can also have a benefit in the San Francisco Bay Area, despite the air quality is generally better. And was interesting that in LA we see a similar reduction of what we can achieve in San Francisco, despite in LA there was no wildfires during the 2020 wildfire season. So we were starting to see also that could be even a co-benefit of using this system for urban pollution. So this is something that we are now digging more in a European founded project that the ESP has an entire work package for working for this. Health Risk Adapt is the name of the project, and I will talk just a little bit about later. So this is the takeaways for this article, and if you want to read a little more, you can go on this QR code, and also all the data analysis is accessible on GitHub. So anybody wants to see the model, improve it, use it, you can go there and see all the model and simulations. And the takeaways are okay, like sheltering indoors is the first thing that you should do, and having a automated system could actually reduce your exposure by 90% compared to be outside. And the central air system can match the filtration efficiency of about 4 portable air purifiers. But you have to account also that there is a bit more energy cost, and about this energy cost is also, well, there are like other things that are interesting about using this automation system and considering the energy resilience of imagine like a constellation of system working automatically for this. The energy use should be accounted in a more, let's say, robust analysis that we didn't do. So to summarize, like people are not using the system. There is a beneficial use of this system that is actually overlooked. So we are like we miss like this kind of using this tool in a better way and eventually use it in an automated way. So we were like doing the extra mile now, and we say this is not published yet, but we say, okay, why don't we build directly this smart thermostat control logic? So consider that we can take inputs from the occupancy if people are or not in the space. We can monitor the indoor PM2.5 measurement, and we can get information from the outdoor PM2.5 measurement if we have open data, or we can install a sensor ourselves. And if we have information about the house characteristic, we can train the model to have an optimized mechanical ventilation runtime. So we did some small field study. So this is a small apartment in the Berkeley, and here you see in the plot on the left you have the concentration of PM2.5 on the y-axis and the time on the right axis, and you have a threshold. This threshold is similar to this 35 microgram per cubic meter, but now I was putting it at 18, and this is something that we can discuss about what is this threshold should be. But here you should see two trends almost overlapped. These are one sensor indoor and one sensor outdoor, and as soon as the outdoor PM2.5 concentration rise, the indoor is keeping at below the threshold by the starting of the automation system. So overall, during this period, you have like you are halving the indoor PM2.5 concentration, and this is consistent with what we were seeing in the model. So we will do this model validation like as a next step. And if what is interesting is that, of course, not only outdoor sources of air pollution are important, also indoor sources are important. And this is when cooking on a pan. So let's say let's say warming up a tortilla or a piece of bread. And this little spike here that is almost not seen is like cooking like a pasta. So cooking with like in a wet environment, let's say environment. And so it's interesting, actually, there is an entire field of study about the indoor air pollution and like activities, behavior, cooking. So it will be interesting also to estimate indoor sources in the model in the future. And this is a detached house, so not a small apartment, our entire residential home. So a bit more complex. There are more people doing things as you have indoor spikes. So probably like this is like probably some cooking events. But what is interesting is that when the system is not running, the indoor and outdoor are the same, are basically matching. So the exchange of air from indoor and outdoor is the same. And when the system is running, you have a lower indoor concentration, and you can see that when the system goes off for some moment, you just rise very quickly to the outdoor concentration. And when you turn it on, you go down again. And for this detached house, it's a bit more complex. People closing, opening windows, you have a less reduction of the impact. And this is interesting because, again, behavior and activities also playing a role here in the exposure. And so to do this, the conclusion of this part, behavior is a very important aspect that we should take into consideration and in this case, for instance, for reducing the exposure to PM2.5, there are a good performance of mechanical ventilation and portable air cleaners that probably are like still untapped and should be used more and in a more clever way, like using also some sensing to control the system, to balancing energy use and health and the health impact. But I just want to spend like a few words on this and not very much, but I think this is also relevant not only if you're considering, let's say, cities and urban environment. This is also important in general, like to talk about the behavior and people in the cities, because despite the cities are only 4% of the European land cover, for instance, is where about 70% of the population live, and the consumption of global energy is about 75%. And the most of the emission came from cities and activities related to cities. And so the environmental co-benefit of increasing the resilience of cities and reaching climate neutral cities, reducing the sources of air pollution and change and let's say improving behavior of citizens, and that could, in my opinion, could be something that we can help and drive through involving them, of course, in the monitoring also of their indoor air pollution, but also by showing them the health benefit of having more sustainable use of resources and energy. Just to make an example about, imagine that we can change the heating system in the Alpine region where people mostly use biomass burning of wood for heating during the winter time, and this is considered like a nice thing to do. And so the next step is do some more field studies for this control logic validation. I didn't talk much about this European project that we are involved, where we are also installing sensor on drones. But I would like to show you also 2-3 slides about this project Health is Adapted. That is actually the evolution of what we are seeing here. And there is more on this if you'll follow this QR code. And what I'm also working now is to conclude this creating this open source tool for monitoring both outdoor and indoor, and do some research industry collaboration. And here I would like to say that it's not the matter of building the monitor or attaching a sensor to a microcontroller and making the data on a computer, etc. Is to create the infrastructure that is making able this sensor to scale. So to be able to install many of them in a way that is sustainable, also a matter of work-wise, and to make this data valuable, because it's not collecting the data on the computer, is actually making the data at open disposal and collecting metadata in a way that makes this data valuable for doing some research, despite we are considering data that are not as good in terms of, let's say, yeah, these are local sensors, so basically you cannot expect them to have the same precision, accuracy of like a reference grade instrument in a lab. And about the model, I'm working now with this within the framework of this Health Risk Adapt to include also PM2.5 sources indoor, and eventually also with Stefania, we were discussing a lot about speciation sources to try to understand also which sources are more impactful in the indoor or considering 90% indoor and 10% outdoor, in order to do this health impact estimation, but also to provide some kind of guidelines for intervention at both, let's say, urban scale or a building scale or like a city scale. And something that we are doing, for instance, is to create this dashboard and to make it open. I think it should be ready by this summer to make it accessible. I hope so. I'm working with this new guy, Lorenzo, that is now assegnista di ricerca. And so the idea is to not only have a map where you can see the real-time data, but also to have a map where you can see the indoor-outdoor ratio and what is happening when you open a window or not. And you can use like a monitor that is easy to install, and as soon as you install it, the data arrive to the database in the right way. And there is like some all this the difficulties of handling all this number of sensors can be handled smoothly and in the more automatic ways possible. And this automation, like having a sensor, a smart plug, or a air purifier automatically running, is actually also something that we are like we want to make it accessible as soon as possible. And here you see in yellow every time the system is on to keep the concentration on a certain threshold, and when something happens, for instance, for an indoor source. And so yeah, so we were discussing also with Juliana about the possibility of making more devices and invite also you if you want to be part of this study. So if you have a house that you would like to monitor and just let me know, and we can try to find a way to spend some money. I hope the CNR will be able soon to spend money of projects to build more of these systems and be able to do this field study for feeding the data on the model. And with Napoli, in case with Enea and Uninapoli and Urban Climate Change as a network, we are trying to bring the model that I did in California into the Italian building environment. It's completely different, and here it's just like a very quick plot in which we have the outdoor air concentration average PM2.5 that Enea was providing at the 4 by 4 kilometers square resolution, and what we can have from the heating point of view and building information that we can get from the database for that the University of Napoli has about energy efficiency of building, that we can extract some infiltration and replicate the work that we were doing in California. And I think that's all from my side. I'm very thank you for your attention. I hope you're still here, and I thanks also all the people I was working recently, and so happy to get to take some question if anybody has.